All right, we're talking about antidifferentiation and indefinite integrals today, and you're like, what? This is so hard. This is something totally new. And it is new, but it's actually really cool. So I don't know if you remember, at the beginning of the year, we kind of talked about that there's two big ideas in calculus. And the first one is the derivative. And it's basically, you know, slope of the tangent line, instantaneous rate of change at a specific point, all of that stuff, right? That's what the derivative is. And the second big idea in calculus is the integral. And so already, right here, we're only in December, and you're already learning, like, the two big ideas of calculus. This is awesome. And the integral is basically, long and the short of it, is it's the area under a curve. So, you know, you have a curve. What's the area underneath that curve for any interval? But it's even cooler than that, because derivatives and integrals are actually connected. And so they're really like one big idea with two parts. So it's like not even two separate things. They're actually inverse operations of each other, which is super cool. So this isn't something new, really. We're just like going backwards. Instead of, like, you know, before we were starting with a function and finding its derivative, now we're starting with the derivative and finding the function. And it's actually really cool, and there's going to be lots of ways that we're going to do that. But I want to show you first. Let's think about, if I gave you this function, not this function, sorry, it's not a function. If I gave you that f prime of x equals 2x, what is the function? If the derivative is 2x, what is the actual function? Well, we've done so many derivatives now that you should be able to go backwards and think, okay, well, if the derivative is 2x, then I know the function was x squared. Are you 100% sure on that? Could it have also been x squared plus 1? Would the derivative of x squared plus 1 equal 2x? I feel kind of like Dora the Explorer here. I'm like, can you say derivative? Anyway, so here we are, finding the derivatives. So if this is the derivative, if 2x is the derivative, the function could have been x squared. The function could have been x squared plus 1. The function could have been x squared plus 100. It had to have x squared in it, and it had to have no other x's, right? But it could have had any constant behind it. So what if I also gave you, excuse me, what if I gave you this function, this derivative? The derivative of a function was 3x squared. What was the function? Well, again, we've done a lot of derivatives, so hopefully you can go backwards and you can see that that would have had to be x cubed. And if you're not sure, if you do it and you're like, was it really x cubed? You can go back and you can say, well, if I have x cubed, I bring the 3 down and I subtract 1, so sure enough, it's 3x squared. But it could have also been x cubed plus 2. It could have also been x cubed plus 1 Google, which is a 1 with 100 zeros behind it, you know. It could have been any of those, right? As long as it was x cubed plus some constant, it would have still been the derivative. So, like, what is the pattern here that we're seeing? What's the actual pattern? If I have the integral, or not the integral, if I have the derivative, let's say that. If I have the derivative and I want to go backwards, what do I have to do to go backwards? Well, let's see. So if I have, like, the derivative is 2x, what would I have to do to 2x to get it back to x squared, right? This is 2x to the first, really. So I had to add 1. I had to add 1 to the exponent, right? Because I have to undo that I subtracted 1. When I'm finding the derivative, I subtract 1, right? The integral is the inverse operation. So when I'm finding the integral, I'm going to add 1. And that would get me to x squared. But what about this 2 out front? How do I get rid of that 2? Right? Because I have 2x, so I add 1 to the exponent, and then I need to divide by 2. So I add 1 to this, and then I divide it by 2. But how do I know what to divide by? So let's look at this one. To get to 3x squared, I have to add 1 to the exponent. So my exponent is now 3, right? So now I'd have 3x cubed, and I need to divide by 3 to get to x cubed. So let's see how that pattern plays out here on some of our problems. Okay, so hopefully that gives you an idea that basically all we're doing is we're undoing a derivative. We're getting given a derivative and we're trying to find the next step back up, right? So it's like those physics problems that you guys love. You're being given a velocity, find the position. You're given an acceleration, find the velocity, right? We're just going up one step instead of going down a step. So let's practice this. Kind of loving this purple pen. I haven't used this color before, but I like it. All right, we're going to differentiate each of the following. So if that's f, then f prime is 3x. If f is x cubed minus 10, f prime is 3x. If the derivative, or if the function is x cubed plus c, where c is any constant number, the derivative is 3x, right? Because the derivative of a constant is 0, so we wouldn't have it. So what would I get when I anti-differentiate 3x squared? So that's basically what we were talking about. We were saying like, okay, oh gosh, I totally screwed that up. I forgot all the squares, and you guys were all yelling at me. You were like, Dora, you forgot the squares. And Dora's over here just going along, going on my adventure, forgetting the squares. Okay, it's 3x squared. I do that a lot. Anyway, 3x squared, 3x squared, 3x squared, right? So the question is, if my derivative is 3x squared, what does my function have to be? Well, we know the function has to be x cubed, but it can have literally any number, any number after it. And so what we do is we do this little thing called the constant of integration. We always add on a constant of integration, and tomorrow we'll come up with, like, maybe we'll name our constant. You can name it, I don't know, Charles or something. But we need to remember, you always got to remember the plus c. You got to remember the plus c, because if I said the derivative of some function is 3x squared, any one of those functions could be the function, right? It could be x cubed, it could be x cubed minus 10, it could be x cubed plus c. It could have been any function, right? And so you have to add that plus c on there because the function is like a family of functions, right? It's maybe, oh, I should have put this on Desmos, but it's like x cubed is here, right? It could be x cubed moved up a little bit. It could be x cubed moved down a little bit. The slope at each point is still the same, right? If I just take that little loop-de-loop, x cubed, right? The slope at every single point is the same, whether I shift it up or whether I shift it down. Same exact slopes. So the function plus or minus a constant is going to have the same derivative. Okay? So this is the main idea. This is the integral. This is the indefinite integral. Da, 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 da. The problem of if this is the derivative, give me the function, is called an integral, right? So an integral is something that it's like, hey, here's a derivative, go backwards and find what the function was. And we write it with this cool little integral symbol right here. It's just like a little kind of like stretched out S of sorts. You'll get better and better at it the more you do it. So it's just like that. And so we would write that if we were trying to ask the question, 3x squared is the derivative of something. What is the function? We would write it like this, the integral of 3x squared dx. Now, that dx is going to be the bane of your existence. You're going to forget it. But the dx is really important because it tells us what variable we're integrating. So it's like what variable does our original function need to be in terms of? Because there's the thing that we don't cover in Calculus 1 called a double integral where you do x's and y's, and so you need a dx and a dy. So those are really important. And when we do u substitution here in a few sections, you'll find that we need that dx or du or d whatever, you know, so that we know what was the original variable we were differentiating. Just like dx dy, right? When we wrote that, the derivative of x with respect to y. That's what where that dx comes from, okay? So, what is the integral of 3x squared dx? Well, it's x cubed plus c. I've got to have that c on there, okay? So that says if the derivative was 3x squared, what is the function? X cubed plus c. So you can read those, the symbol, integrand, blah, 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 constant of integration. Don't ever forget your constant of integration. We're going to really, really, really work hard on that. The plus c is like one of the most commonly forgotten things. So like circle this, put like little stars by it, and write things like Mrs. Barney will kill you if you forget. I won't. But got to remember the constant of integration, okay? So here's our rules. Did you see, remember we had a pattern before, and we said, well, if we start with, if I have this, say 3x squared is my derivative, and I want to go back to my function, I had to add 1 to the exponent, and I had to divide by 3. And so the question is, how do I know what number to divide by? Because you don't always divide by like this number out front, right? This is the general rule for integrals. You add 1 to the exponent, okay? You add 1 to the exponent, and then whatever that number is, once you've added 1, you divide by that same number, right? So if I had 6x squared, I add 1 to the exponent, and I divide by this number right here. I divide by this number right here, okay? So I divide by 3, and I end up with 2x cubed. So if I want to find the integral of 6x squared, it would be 2x cubed, and that would make sense. Let's see. If I take 3, if I derive this, 3 times 2 is 6, and then I subtract 1, which is 2, so it really is 6x cubed. So let's see why I do that. So that's the power rule. The constant rule basically says that the derivative, or the integral of any constant, is just that constant times x, which makes sense. Okay, so let's go back, and let's think about if you had the derivative of 3x. I want to find y prime of 3x, right? It's just, sorry, not y prime does not equal 3x. I want to find y prime of it. Y prime, if this is y prime equals 3, right? So if I want to go backwards, anytime I have a constant, we know that there was an x there before, and so I just tack that x back on, right? So the integral of 3 dx would be 3x plus c, okay? All right, scalar multiple rule. If you remember with derivatives, anytime we multiplied something, we could like take the derivative without multiplying anything, like without putting the constant in the derivative, and then we could tack it on later. Integrals are the same thing, right? Like if I had something like if I had you know 2/7 x squared, and I'm like, ooh, well, I could just, this scalar can, if I want to say the derivative of, or the integral of that, I can just take the 2/7 outside the integral. I can take the integral of, I should have dx on here, the integral of x squared dx, and then just multiply whatever that integral is by 2/7. You know, and that helps so much, because there's a lot of times you need to just pull that constant out. And the last rule that we're going to talk about before the next video is the sum rule. Oh, actually, really quick, never, ever, ever factor out a variable. Ever, 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 ever. 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 Okay, last one. The sum rule is the same. Like, if I had x squared plus 3x, I could derive each one of those individually, Integral is the same thing. I could go the integral of x squared plus the integral of 3x.